So hello everyone, this is our fifth tutorial. Today we'll discuss on those topics, that is vectors or characteristic vector, whatever you say. So those are our topic of interest. So if you see the first question, so here V is a vector, VB is the vector space of all polynomials over R, and F is a linear functional. It is defined by FP is same as integration 1 to 3 px dx, and also a polynomial px is given. The question is for the differential operator d. So we know here in this case V is the vector space of all polynomial. So we may denote it by P. So it will contain all those polynomial summation ai x to the power I, where I is from 0 to some n. Okay, ai belongs to real number and n is some fixed integer, preferably non-negative integer. So this is our vector space. Now we need to find uh, d transpose F applied on P. So first let us see what is the meaning of transpose. So given any linear operator T from V to V, we can form a dual. That is, what is the meaning of dual? It is denoted by V star. It means of linear functionals. So it will look like any vector from V star. It will look like a linear functional from V to R, V to the given field. In this case, it is R. Now, if we take any such functional f, so we have a map from f to V to the given field f. Then clearly, if we compose with this transformation, linear transformation, we'll get a map from V to F, right? Therefore, what is the map we are getting? It is simply F compose T. This is the map. Therefore, for any such linear operator, we can define a linear operator from this codomain. Corresponding to this codomain, we get a V star. Corresponding to domain, we get a V star. And we can define a linear map from this to this. That is, corresponding to this, we are taking V star, right? So, and what is the definition? Take any functional f, map it to f compose t. So this f compose t, clearly it is a linear functional from V to f. So thus we get a linear functional, that is another linear operator between those two dual space from V star to V star. So in this question you can see what is DTF. D transpose A. If we take D transpose F, what it will be? So corresponding to T, we denote it by T transpose. Okay, and why the notation transpose arise? It is because if you take property of transpose, so if you take a linear if you take the matrix representation of T, representation of T with respect to basis B, if it looks like some matrix, suppose this T with respect to basis B, it looks like some matrix, uh, suppose this is a matrix P or whatever your favorite matrix A, then T transpose with respect to the dual basis. So dual basis we already know, right? If alpha 1 up to alpha n, this is the basis B, then we get a dual basis B star. It will look like alpha 1 star up to alpha n star, where alpha I star is defined by alpha I star acting on alpha j. It gives you, that is, it is defined as 1 and 0. When I is same as j, it is 1, and otherwise it is 0. Okay, so if you want to get a matrix representation of this transpose operator with respect to this B star dual basis, it will look like A transpose. That's why it is the motivation of this name comes from. Now we need to find D transpose F. Back to this question. So let us draw the picture again. Sorry. Okay. So for this question, let us draw the picture again. Here D is an operator from V to V. V is the polynomial space. And now, given a linear functional f, right? F is a linear functional. Is there any problem? Sorry, network is low. Right. Okay. So the linear operator is defined by differential. So here so P is the given polynomial. This is Px. It is defined by 1 minus x plus 3x square. So if we operate via D, so D 1 minus 1 plus 6x, just taking the differential. Now we apply f, right? So we go f. So f is defined by taking integration. So this, so we'll integrate this dp by definition. So it is minus 1 plus 6x integration from 1 to 3 dx. Clearly this is minus x plus 6x square by 2, which is 3x square. Now put the value 1 to 3. So this will be minus 3 plus 27 minus minus 1 plus 3. So this value is 24 minus 2, which is 22. Therefore it is clear, right? We have taken the element px and simply first we applied the differential. So applying differential we get minus 1 plus 6x. Now applying the linear functional we get the desired thing. So this is our d transpose f applied on this d transpose f applied on the polynomial p. Okay, I think there is an issue with the notation, that is, no, it is okay. So f is an element from the dual history. It is okay. So by definition, recall this is d transpose fp. By definition, you can see this is same as so t transpose applied on f. It see from here t trans applied on f. It is same as f compose t. Right now, if you apply f is a map from v to r. So if you take any element v from this, so t transpose fv, this is same as f compose t of v. That is what we have done. T transpose fp, instead of vector v, here we have a polynomial p. So this is by definition f compose d applied on p. Just see the relation between those two things. We have done the same thing, right? This is same as f compose d. The calculation gives the f compose d. So the answer is 22. Now question number 2. Here the vector space V, it is the space of all n cross n matrices over the field F, and T V the linear transformation on V. So it means T F. Now for a fixed D in B V, T transpose denote the transpose of the transformation T, then and let F be the functional on V, F equal to trace. So again it is similar question. What we'll do, again T transpose F applied on A, again if we follow the definition, this is same as F compose T applied on A. This is what we have seen. Simply if we draw the diagram, it will be more clear. We have a linear operator V to V, T from V to V, and given there is a linear functional F which maps this V to scalar field F, right? So by definition, if we start with an element A, then we have TA. By definition, TA is same as BA minus AB. And F is same as taking trace of the matrix A. Therefore, if we start with some BA minus AB, then if we take trace of this FTA, this is same as taking trace of BA minus AB. Right? But you know, trace of AB is same as trace of BA. So this is same as trace of BA minus trace of AB. But their trace are same. TR denotes trace here, okay? So those trace are equal, therefore this becomes 0. Hence the answer will be, you can see this is same as 0, we get F compose T. This is therefore this is 0. Hence the option will be A. Okay. Okay, there is some lag. I don't know what is the problem. Let's continue. Some network issue. Now, next question, that is question number 3. Here you can see the linear operator T is on R3. That is T is a linear transformation from R3 to R3. And representation of T with respect to standard basis B, it is given by 2, 1, 6, minus 1, 0, minus 1, minus 2, minus 1. We need to find characteristic value or eigenvalue of this matrix. So how do we find eigenvalue? Let A be the matrix. Then eigenvalue can be found obtained by the characteristic polynomial. So let me write the characteristic equation. The characteristic equation, it is denoted by chi A of x, which is same as chi A of x equal to 0. But characteristic, it can be explicitly written as determinant of A minus xi equal to 0. So we need to find the determinant of A minus x. So if you subtract x from the diagonal, we get the matrix A minus xi. It will look like 1 minus x. Then again subtracting from the diagonal, minus 1 minus x, again minus 1 minus x, and rest of the things are unchanged. So this determinant is 0, and all the characteristic values or values, those are obtained from this characteristic polynomial. That is, we need to solve this equation. Okay, so let us try to solve this. Clearly, it is it is easy to see that if we find the determinant with this third column, it is easier because there is some 0. So it is same as 1 times 6 minus 1 minus x minus 1 minus 2, and then 0, and then plus minus 1 minus x times these two things, right? These two column delete, so this. 1 minus x to 6 minus 1 minus x. So this equal to 0. Now this is same as minus 12 plus 1 plus x minus x plus 1 times. So here we have x minus 1 whole square x square minus 1, because those are in opposite sign, minus 12. This is same as 0. And now this is same as x minus 11 minus x plus 1 times x square minus 2x minus 1 plus 1 minus 12. That is again minus 11 equal to 0. Simply we just compute the calculation. But the second thing is minus, so minus x cube, then and again plus x square, so it is minus x square, then minus 11x and minus 2x, that is minus 13x, then minus 11. This is 0. So you can clearly see that minus 11 minus 11, those are cancelling each other. So the equation reduced to, if we take x common, then we get x cube. X cube means it will become x square. So instead of writing this, let me again write. Just will multiply with a negative sign, which will give us x cube minus x square minus 13x, and there will be minus x, that is minus 14x. This is 0. So from this, taking x common, we get x square minus x minus 14 is 0. So what are the solution of this equation? You can see that x this will give either x equal to 0 or x square minus x minus 14 equal to 0. But if you factorize this, is it okay? X cube x square plus x minus 1. There is some mistake. There is some mistake. Yes. Okay, so let me check my calculation. So first one is minus 12 and then minus of this, because determinant means this times this minus this time this. So there it is 1 plus x, but we need to take negative sign of this. Those are, so you should be careful here, otherwise it will be wrong. Determinants of ABCD, it is same as AD minus BC. So there is negative sign. And similarly, after this, everything is okay. Okay, so let me correct. This is actually x minus x plus 13. Minus x minus 13. That is, we can write minus 13 minus x. And after this, it is, oh sorry, this is actually x square minus 1, not x minus 1 whole square. So this is actually simply x square minus 13. I've done this mistake again. So x square minus 13. Okay, then it is much easier. Okay, sorry. So you can um, okay. So you can again expand this. We get just x plus 13 multiplied by a negative sign. So it becomes plus of this. So x cube minus 13x plus x cube. Then it is x squared plus x squared, and then minus 13x minus 13 equal to 0. So 13, 13, those are getting cancelled. So we get x times x squared plus x, that is minus 12x, right? Minus 12 x square, if we take x common, then it is plus x minus 12, it is same as 0. But again we can factorize this, so we get x. So this equation gives x equal to 0, or another possibility is x square plus x minus 12 equal to 0. So again you can factorize, because um, plus 1 can be written as 4 minus 3. So if you factor this plus 1 here, you get x plus 4 times x minus 3 is same as 0. So you get three possibilities: either x equal to 0, or other two possibilities are corresponding to the last thing, either x equal to minus 4 or x equal to plus 3, right? So those are all possibilities. Minus 4 plus 3 and 0. So minus 4 plus 3 and 0. So this is the correct answer. Okay. So next question. This is our question number 4. Here it is M2R, that is the space of all 2 by 2 matrices. Trace is minus 2 and determinant equal to plus 2. Now the question is, we need to find uh, these operators corresponding this operator TB equal to BA. We need to see if those are true or not. Okay. So for those kind of problems, that is, in this case we need to find Eigen values or diagonalizability. For those kind of problem, first we'll obtain a matrix representation of the operator T. There are different approaches, but let me do in this way. So we know what are the standard, what is the standard basis for M2 by 2. Any matrix will look like this: A, B, C, D, right? So standard basis of M2R, sorry, this is M2R. So M2R, the standard basis of M2R, this is same as E1, E12, E21, E22. What are those elements? E11 denotes one entry is 1 and other entries are 0. Similarly, 12 denotes 1/2th entry, which is here, it is 1 and other things are 0. E21 is similarly 0, 0, 1, 0. E22 means 0, 0, 0. So from here, if we apply T on any element B, suppose suppose B is this element. Okay, let B equal to B 1 1 1 2 1. That is in one word. It is B I J. Okay, IJs are from 1 to 2. Maybe write explicitly for the calculation. So it is simply multiplying with A. T applied on B is multiplying with A. So instead of writing B, we write A because we actually need A. We are multiplying with the element A. So let me write, instead of B, let me write A. Okay. Now we need to see what is T applied on B. So T applied on B, it is given as B times A. Right. Therefore, if we apply T on E11, it is same as multiplying this 1000 with, that is T E11. By definition, this is same as E11 times, this is E11 times A, right? And A is, we chosen A to be this A11 12, A21, A22. So if we calculate, this is simply first row. Multiplication will give me first row because there is 1 0. So it will give me first row, and 0 0 means 0 0 combination. So it is second row. Now we can see this can be written as A11 times U1 plus A12 times E12. And by the similar calculations, E12, it is simply, it will take the from the second row on the first. So it is A21, A22 and 0 0. It is easy to see. Otherwise, just multiply, you will obtain this thing. So this is same as A21, E11 plus A22, E12, and rest of the thing are 0. So we may write, because we are uh, trying to find matrix representation, we may write the other coefficients. So those are actually 0. Right? Plus 0 times E21 plus 0 times E22. And uh, multiply T applied on E21. This is simply, it will look like 0 0 times 0 0 1 0 times that same A11 A12. So it is same as taking the first row of this A. So it is A11 A1, and the first thing are 0, right? So you can see this is now, there is no coefficient of E11 because this element is 0. Similarly, there is no coefficient of E12, so those are 0. But coefficient of E21, this is A11, and E22 coefficient will be A22. Similarly, you can write T22. This is same as 0 0, and there will be A21 E21 plus A22 E2, right? Therefore, matrix representation of T. So basis by B. This is the basis. Okay, basis of the M2R of this vector space. So matrix representation of T with respect to this basis, it will be same as we just put those coefficient in column. So the first column, let me mark this. So this is the first column will be coefficients. So it will be, we need to put in the first column. So it will take the form A11, A12, A. So there is no coefficient is 0, so it is now 0. So this is 0. Similarly, coefficient of E22 is 0, so 0. Similarly, if we see this, then it will be A21, A22, 0, 0, then A11, A22, 0, 0, A21, A22. So matrix representation of this transformation, it will take the form A comma A, right? Because A denotes this matrix. So A comma A and non-diagonal entries are 0 by 0 matrices. You can see this is a block diagonal matrix whose diagonal are A and rest of the things are 0. We have just written those things. So if you practice those kind of problem, you can easily see this will take the from those kind of diagonal block diagonal matrix. Now we need to find eigenvalue of this T. So finding eigenvalues of T is same as finding eigenvalue of its matrix representation. So we need to find eigenvalue of this matrix representation. So denoted by T or maybe Q. So instead of PQ, let me denote it by A is already there. Okay. So this let this is P. So we need to find eigenvalue of this P. Okay. So eigenvalue of P, it is obtained from this equation. Determinant of P minus xi equal to 0. Right? It is same as if you write all those things, it is same as A minus xi. Things are 0, we just subtract from the diagonal. But this determinant is same as, we can easily expand this determinant, right? This is same as determinant of A minus xi times determinant of A minus xi equal to 0. So this is same as determinant Okay, everything is okay now. So all the eigenvalues of P, it can be obtained from, that is, it is same as eigenvalues of A. Okay, because it satisfies this relation. This is same as X is eigenvalue of A. X is an eigenvalue of P. Eigenvalue of A. So from here it is clear that all eigenvalues of P obtained from eigenvalues of A. But what are the eigenvalues of P? Eigenvalues of A. It is given that trace of A is -2 and determinant is 1. So trace of A is -2 and determinant of A, it is 1. But we know that sum of the eigenvalues, so there can be two eigenvalues because it is 2 by A is 2 by 2 matrices. Therefore, if x1, x2 are eigenvalues of A, then their sum is x1 plus x2. This is -2, and their product is 1. Okay. Instead of writing this, we may write, we can write in this way. So if x is an eigenvalue, then another trace is -2. So we know that sum of eigenvalues equal to trace. Okay, and product of eigenvalues is same as determinant of A. Eigenvalues of A. Okay. Then from the first thing, if x is an eigenvalue, then another eigenvalue trace A is same as -2. So sum is -2. So if x is an eigenvalue, then another eigenvalue is -2 minus x. Right? And similarly, their product should be, determinant is given as 1 in this case. So those are given. Now from those two things, we get x times -2 minus x. This is same as 1. Now this is same as x square plus 2x plus 1 equal to 0. That is x plus 1 whole square equal to 0. Therefore, there are two solutions, both are same. That is multiplicity of -1. The solution is 2. It occurs twice. So eigenvalues of A is -1. Therefore, eigenvalues of P, this is also -1, because we have already seen that eigenvalues of P is same as eigenvalues of A, right? Therefore, we get the answer. Both are same. Eigenvalues of A and P both are same in this case. Okay, it is restored. Okay, next question. Oh, we have not solved completely. So here that 2 is not eigenvalues of P, because we have seen the only eigenvalues of Okay, internet is bad. You can connect with this. Okay. Okay. So as we have seen that -1 is the only eigenvalue. So 2 cannot be eigenvalue of t. So this is false. Now t is not invertible. When t is not invertible, when this occurs, t is not invertible. This means there exists 0 is the eigenvalue of t. Why? Because t is not invertible means there exists some vector v such that t times v 0. T is not invertible means t applied on some vector, it will be 0. Kernel contains something. It cannot be injective. Invertible means this. So t of v equal to 0, same as 0 times tv is same as 0 times v. That is t. That is 0 is from here you can see that 0 is an eigenvalue of t. But we have seen 0 is not eigenvalue of t because -1 is the only eigenvalue in this case. Right? We have already seen that -1 is the only eigenvalue. So this is also false because 0 is not eigenvalue of this of t. And tb equal to pv. Is it possible? tb equal to b, again tb equal to b means t minus uh, t minus I times b equal to 0. But it is true for some non-zero b. But this means t minus, you can see that t minus I times b equal to 0. That means determinant of the operator t minus I, this will be 0, which means determinant of the matrix P or matrix representation P minus I equal to 0. And it means 1 is eigenvalue of t, P, EV of P, eigenvalue of P, which is certainly false because we have seen -1 is the only eigenvalue. So this is also wrong. The next thing is t is diagonalizable. Uh, okay, here we have seen uh, the only eigenvalue of t is -1. So again, we cannot say if t is diagonalizable or not, right? So we cannot say it. It mean it. It is possible that A is not diagonalizable. So if A is diagonalizable, then this t is also diagonalizable. Okay. So though this is not given, if there are two different eigenvalues of A, then we can certainly say that A is diagonalizable. Oh, what is the problem? Okay. So if two different eigenvalues occur for A, then we can say that A is diagonalizable because two different distinct eigenvalue will give two different eigenvectors. and this is the condition for diagonalizability. That is, if A is n by n matrix and we have n distinct eigenvector, then A is diagonalizable. But here we cannot say if A is diagonalizable or not. So there, T is diagonalizable or not. It depends on if A is diagonalizable or not. So those three are certainly false, but we cannot conclude from this. So what about diagonalizability of? So let me write A is diagonalizable if and only if A is n by n matrix, if and only if there exist n distinct, not distinct, n linearly independent eigenvector. So this is always true. This just remember that this is true, because what happened? What is the meaning of eigenvector? Eigenvector means, so if there is some non-zero vector v, this is said to be eigenvector if AV is same as some lambda times v. Okay, lambda is some scalar. Then v is said to be an eigenvector. And if those lambda 1 up to lambda n are distinct, let me show why this is true. If lambda 1 up to lambda n, there are n distinct eigenvalue, if there are n distinct eigenvalue, we have so we need to prove that there are n distinct eigenvector. So corresponding to fd lambda 1, we get at least one eigenvector v1 up to vn. Now we need to prove those eigenvectors are linearly independent. So if possible, let their combination some ci vi, this is 0. Then if we apply a on the whole thing, then we have a times sum of ci vi, this equal to 0, I equal to 1 to n. Okay. So this means, again by linearity, it is same as a times vi equal to 0. But a times vi means vi are the eigenvector corresponding to the eigenvalue lambda. So a vi is same as lambda I vi, right? So we get sum of ci lambda I vi, which is same as lambda I times ci vi equal to 0. Similarly, if we again apply a, we will get another equation, lambda I square ci vi equal to 0. And if we continue, then last equation will be lambda I to the power so there we can continue the process, but finally we will get lambda I to the power n minus y, lambda I to the power n minus 1 ci phi equal to 0. And now we can see the coefficients of ci phi. Those will form a matrix. So here the coefficients are 1, so it is 1 1 up to 1. After this, here the coefficients are lambda, so it will look like lambda 1 up to lambda n. So 1 1, lambda 1, lambda 2 up to lambda n. Similarly, the last equation, it gives the coefficient lambda 1 to the power n minus 1, lambda 2 to the power n minus 1 up to lambda n to the power n minus 1. Now we can see the determinant of this thing determinant, it is non-zero, because this is actually van der Waals matrix, and you have already, you should be able to prove that determinant, it will look like some kind of product lambda I minus lambda j. But here it is given that lambda I and lambda j, those are pairwise distinct. Okay. Therefore, this product cannot be zero. So this product is non-zero. This will imply each of Ci Pi are zero. This is true for all I. And Vi are non-zero vector. This will definitely imply Ci equal to zero for all I, since Vi is non-zero. By definition, eigenvector cannot be zero. Okay, so from here we can say if there are two different eigenvalues are given, then we can say this is true, that the T, the given transformation, it is diagonalizable. Diagonalizable means P inverse AP in this A is said to be diagonalizable if P inverse AP is identity matrix, n by n identity matrix. Okay, so there are two cases. Two cases will occur. If A is diagonalizable, case 1, A is diagonalizable given or not. A is diagonalizable. So A is diagonalizable means P inverse AP is the diagonal. That is a diagonal matrix. Diagonal matrix means it will take the form D1 up to Dn. So diagonal entries and other things are zero. Now P inverse AP is diagonal. This will imply, if you take sorry, instead of P we should write another things, because we have already used P. So let me write Q inverse AP. Suppose Q is matrix, then if we use block diagonal matrix, then we this block just multiply inverse of this first inverse of this block, it is Q inverse Q. So we get a diagonal matrix. So the last is if just speak. So it is the conclusion cannot be drawn in this case. So if so this is none of the above. For this question, this is actually none of the above. The answer is none of the above. Now let me solve this problem. Here A is 3 by 3 matrix with real entries. So A takes the from this 3 by 3 matrix A11, A12, A13, and similarly other entries. And all entries are real. Now A is necessarily diagonalizable over R. So let me see something. Let A equal to this 1 1 1, and above the diagonal the entries are 1 and everything are 0, every other thing. So you can see, or yes, so you can see that if we solve the equation determinant of A minus xi equal to 0, then it is clear that it will take the form 1 minus x, 1 minus x, and other things are same, equal to 0. But if you expand, this is same as 1 minus x whole cube. Just expand with respect to the first column. Okay, this is easy to see. Okay, so 1 minus x cube equal to 0. This will imply x equal to 1. So if you see those kind of upper diagonal or lower diagonal, upper triangular or lower triangular matrix, then eigenvalues are the diagonal entries, right? So here you can see all those diagonal entries are 1. That's why we get all those eigenvalues are 1. Now, can you see that this A cannot be diagonalizable? So if A is diagonalizable, then we need 3 distinct eigenvectors. We have already seen that diagonalizability it depends on the fact if there exist n linearly independent Li eigenvectors. So you can see in this question, it is 3 by 3 matrix. Okay, A is n by n matrix in this case. So it is 3 by 3 matrix. We need at least 3 linearly independent eigenvector. So let X be an eigenvector. Sorry, P. P is an eigenvector. Then it will satisfy the equation A minus lambda I. Here lambda is 1. So it is A minus 1 times I into eigenvector satisfy the equation A minus lambda I times V equal to 0. Okay. So A minus lambda I times V. So let V equal to this. V takes the form B1, B2, B3. This is the eigenvector. So A minus lambda I V equal to 0. But A minus 1I, if you subtract 1 from the diagonal entries, then it will take the form 0, 0, 0, and other entries are not changed. Those are fixed. So we are only subtracting from the diagonal, and we have assumed B is same as B1, B2, B3. So this is 0 matrix, but this implies that B1 equal to 0, and the second thing will imply B2 equal to 0. So B1 and B2 equal to 0. So the therefore the only possible eigenvector corresponding to 0, eigenvalue 0, this is the eigenvalue. It takes the form B1, B2 are 0, but B3 can be anything, right? So it is spanned by this vector 0, 0, 1. Linear span of this vector. 0 0 v3 where v3 belongs to the field. In this case, field is R, or any field, or whatever field is given. So from here it is clear that there is only one linearly independent eigenvector, right? So since there is only single linearly independent eigenvector, we cannot get three eigenvector, which is necessary and sufficient condition for diagonalizability. So there is only one eigenvector. So this is false. It cannot be diagonalizable. Now another option, if we see, if all the eigenvalues of A are non-zero, then it is diagonalizable over C. We have seen that all eigenvectors are 1 1 1, which is non-zero, which are non-zeros, but still the uh, there are no sufficient eigenvectors. We have only single eigenvectors. So this is also false. It is not diagonalizable. We have already seen this case. Now the third thing is A has distinct real eigenvalues. If A has distinct real eigenvalues, then it is diagonalizable. Is it true? Okay, let us see. We have already seen that if A has three distinct real eigenvalues, if A has distinct real eigenvalues v1, v2, v3, those are distinct real eigenvalues. So distinct means v1 not equal to v2. Those are pairwise different. So v not equal to vj for all I not equal to j. This is given. Now clearly for v1 will instead of v1 lambda we write lambda 1 for eigenvalues. The notation is lambda 1 lambda. So lambda is not equal to lambda j. So for lambda 1 we get eigenvector v, at least one eigenvector. For lambda 2 we get another eigenvector v2. For 3 we get another. So by observation in the previous problem, we have seen that v1, v2, v3, those are linearly independent. So linearly independent means we have n linearly independent eigenvectors. So this is diagonalizable. But the problem is we don't know if it is diagonalizable over R or not, because in general it is diagonalizable over C. Okay, but we don't know yet if it is diagonalizable over R. But if we see, since A is real, it is already for option 3. A is real 3 by 3 matrix. Therefore, if v1 is an eigenvalue, then it satisfies A v1 equal to same as lambda v1. Lambda 1, that is v1 is solution of this equation A minus lambda 1 I times v1 equal to 0. We can see lambda 1 is real, A is real, so it is a real 3 equation, right? There we have already seen those. If those coefficients are real, then the equation will be some the equation will have real coefficients. For example, b1, b2, if we see that those are coefficients of those entries are real, so clearly those are real coefficients. Therefore the solution obtained from this equation must be real. So from here we can say that v1 is real, that is eigenvectors are real. So similarly all those other eigenvectors are also real. So if A is real given, then this is true. Okay, A is real and distinct real eigenvector. From those two things, we can conclude that this is diagonalizable over R. And C is already correct because we have already told that A has distinct eigenvalues. There are three distinct eigenvalues, so we have three distinct eigenvectors also. Therefore, it is diagonalizable. So C is also correct. Okay, let us solve question number 6. It is given that A is real symmetric matrix. Then we need to see if those are correct or not. First question is A does not have 0 as an eigenvalues. But we know that just take the 0 matrix. 0 matrix. Okay. For in particular, let us consider only 2 by 2 matrix. If we take the 0 matrix, the eigenvalues are 0. So this is certainly false. Okay. All the eigenvalues of this example, it is symmetric because 0 transpose is same as 0. Now, if A inverse exists, then A inverse is also real symmetric. Is it true or false? Let us check. So, given A is real, then clearly if inverse exists, then A inverse is also real. If exists. Because if A inverse is some complex matrix, then clearly A times A inverse, that is A is real and B is complex, then A times B, this will be always complex matrix. Okay, because you can check with the first entry, that is A times B, the 1 entry of A times B, it is always complex. So if A is real, if inverse exists, then it must be real. Now the question is if it is symmetric or not. So this is what we need to check. Okay, given A transpose equal to A, then it is given that inverse of A exists. So there exists some B such that A times B with is same as B times A is identity. It is given. Since inverse exists, we have such a matrix. Now if we apply transpose, AB transpose is same as B transpose A transpose. Similarly, BA transpose is same as A transpose B transpose. And this is I transpose is identity. So we get from here, it is clear that sorry, what is okay? It is given that A transpose is same as A, right? So B transpose, from here we get B transpose A is same as AB transpose, which is same as I. So from here it is clear that inverse of A is also A inverse is, because B transpose also satisfy the condition. From here it is clear that A inverse is also B. But inverse of a matrix, if exists, always unique, right? Therefore, by uniqueness, B transpose is uniqueness of inverse. Since we have already assumed that B is inverse of A, that's why we are getting that equation. Okay. So from here it is clear that B transpose, that is, but B is the inverse of, so B is inverse of A, so A inverse transpose is same as A inverse. Okay, so this is true. Now A has at least one positive eigenvalues. A has at least one positive eigenvalues. So again, this is false. Why this is false? Because take the matrix for C, option C, take the minus identity, which is minus 1, and 0, 0. So from here, diagonal entries are minus 1, and I have already said that for any diagonal matrix or any upper or lower triangular matrix, eigenvalues are diagonal. It is just a simple observation. Just from determinant calculation, it is very simple to see. So eigenvalues are, in this case, eigenvalues are minus 1, those diagonal entries, minus 1, minus 1. Therefore, determinant eigenvalues can be negative. All eigenvalues can be negative. So this is false. This is false. Next option is all eigenvalues of A are real. So it is also false. Let me give an example. Okay. So if we take this example, 0, 1, 1, 0. This is symmetric, right? But if we try to find the eigenvalues, let A equal to this, then determinant of A minus xi, this determinant is 0. This means just subtract x from the diagonal and everything is fixed. This is same as x square. Sorry, this is not working. This will give x square minus 1 equal to 0. So this is actually not working. So is it true that all eigenvalues of A, okay, A is symmetric matrix, right? So it is true. Let us see why this is true. A is symmetric matrix, so let lambda be an eigenvalue of A. Then there exists some V, non-zero V, such that non-zero vector such that AV is same as lambda V, right? If we apply conjugate transpose, then we get AV bar transpose, which is denoted by this notation node, is same as lambda V bar transpose, or maybe just apply bar transpose, conjugation and applying transpose. So again, conjugation also behaves similar to applying transpose. So this is V bar transpose, then A bar transpose, which is same as V bar transpose, then lambda bar transpose. But lambda bar is scalar, so it is just multiplying with lambda bar. One by one, you can thought as lambda bar is 1 by 1 matrix type of thing. So, but A is real matrix. So A bar is same as A. And also A is symmetric. Therefore, from here we get A bar transpose is same as A transpose, but by symmetry A transpose is same as A. So from here we obtain V bar transpose A is same as lambda bar V bar transpose. Right. Now what can be done? Simply multiply V. So multiplying V on the right, so we got V bar transpose AV is same as lambda bar V bar transpose V. But AV is same as lambda V. Okay. So if we denote it by star, we can write as lambda v. AV is same as lambda v. Okay, v bar transpose. This is same as lambda bar v bar transpose v. But we know v bar transpose v is same as, it is non-zero, always non-zero thing. V bar transpose v is always non-zero. You can easily check with any example. If you take any complex vectors, and if we, of this form g1 maybe b1 up to bn, those are complex vector, and if you multiply by its conjugation transpose, it is always negative, because of the simple fact that any entry bi bar into b multiplying it with complex conjugation is same as mod of bi square. So all entries, it will give sum of mod bi square. So it is certainly, this is non-zero. Since v is assumed as non-zero, otherwise it is not true. Right? We have already assumed this is non-zero vector. So this is same as, so take lambda v bar transpose common, then we get lambda minus lambda bar equal to 0. But this is non-zero, therefore the second thing must be 0. So lambda minus lambda bar equal to 0. That is, lambda is same as lambda bar. But when this is possible, so suppose lambda equal to some a plus bi, but lambda bar will take the form a minus bi. When those two things are equal, what is the condition? It must imply, so those two are equal means a will cancel out, so it will means bi is same as minus bi. But if b is non-zero, then negative cannot be equal. Therefore, we must have b equal to 0. That is, complex entry is 0. So it means imaginary part of lambda equal to 0. That is same as saying lambda equal to real. So every eigenvalues of symmetric matrix is always real. So this is also true. So we obtain that C answer of this problem. This is, we obtain D and B. Those are the answers. Now consider this problem. Here Px is given as this. Okay, maybe turn on the video. Okay. Okay, let me turn off, otherwise it will make problem. So Px is given matrix. Now we need to check what are the possibilities. If it has zero eigenvalue 0 or not, for some x or for all x, or what can we say? So what is the how can we find eigenvalue? So x is already used, so let lambda be an eigenvalue. If lambda is an eigenvalue, we can write determinant of p minus lambda I equal to 0. But this means 1 plus x square minus lambda 7 1 3x 2x minus lambda, just subtract from the diagonal 4, and the rest of the thing are fixed. This is 0, right? So if 0 is an eigenvalue, then putting lambda equal to 0, this will be satisfied. Then determinant of p minus 0I will be 0, right? That is same as determinant of p equal to 0. So instead of writing all of these things, we can simply write data 0 is an eigenvalue. This is if and only if this determinant should 0. 1 plus x square 7 1 3x 2x 4 8x 7 3. This should be 0, but this determinant should be 0. Determinant of px, this should be 0. But let us expand this determinant. Okay, so simply what can be done? To simplify, we just subtract, we apply the operation C2 minus 7C1. For those kind of operation, if we apply those kind of operation, determinant remains same. So first column is unchanged, second column is 7 minus 7, it is 0, x minus 28, 7 minus 21, that is minus 40. Only 143. Now we'll expand the determinant with respect to first row. Okay. So expanding, we have 1 plus x square times 2x minus 28, 4 minus 14 3 plus 1 times 3x minus 14, x minus 28 and 8x. Oh, sorry. So same problem. So this is same as, this is equal to 1 plus x square times so we can take 2 common, so that it is much easier. Otherwise, let me calculate 2x minus 28. Is it 28? Yes, 2x minus 28. 2x minus 28 times 3 minus 4 into 14, which is 4 into minus 14, 56. So it will be plus 56. Okay, plus minus 42x minus 8x times 2x minus 28. Okay, all right. So this is same as, so you can take 2 common. So it is same as 1 plus x square times 3x minus 42 plus 50 plus 28. So it means 3x minus 80 plus 2 is already taken, so it is minus 21x and then minus 8x, right? That is minus 29x, and similarly plus 28, so it will give plus 14. So from here, coefficient of x cube, we can see coefficient of x cube is same as 3x into x square, so it is times 2, so it is 6, right? 3 times 2, it is 6. So in general, this is non-zero. This is non-zero because coefficient of x cube equal to 6, so this is non-zero for, it cannot be 0 for all x. Okay, for some x we have it can be 0, so it is third degree polynomial. So we have three solution of this, this equation star. So for those three values, of x, this determinant is 0, det of p is 0, right? For those three values of x, det of p equal to 0, det of px equal to 0. So this is, so from here it is clear px has eigenvalues for some x. So there are three different possibilities of x. So those three can be also same. There any two of them can be same, but there are few possibilities for which determinant px equal to 0. That's why 0 is an eigenvalue of px. For all x, we have seen for all x, this px may not be 0. Determinant of this px is not 0. In general, this is not 0 for all x. For example, because the coefficient of x cube is 6, so it cannot be 0 for all x, right? So this is false. 0 is not an eigenvalue of px for any x. So this is also false. We have seen there are three possibilities. All may not be different, but there is some possibilities for which determinant is 0. Three solution of the equations. So this is also false. Px is invertible for every x. No, this is also not true because determinant of px equal to 0, it occurs for some x. For some x belongs to 1. Therefore, corresponding to those, so for those px, determinant is 0. Right? Therefore, this is also false. It cannot be in determinant px equal to 0 means it is actually not invertible. It is not invertible, but it says that it is invertible for all x. So this is also false. Now let us solve question number 8. This is an interesting question. So J is the matrix. It is defined as 51 by 51 matrix and all entries are 1. Okay, those are all 1. This is the matrix. Now the question is we need to find determinant of J minus I. Okay. So instead of let us find what is the determinant of J. So if we find sorry, not determinant, what are the eigenvalues of J? Determinant of J is certainly 0 because rank of the matrix J is 1. All other rows are linearly dependent. It can be written as linear combination of the first row. So rank is 1 and therefore determinant is But if we let us see what are the eigenvalues of eigenvalues of J. So we want to find this. Okay. Instead of finding eigenvalue, what we can do, okay, let us see. So certainly 0 is an eigenvalue whose multiplicity will be 50 and multiplicity, algebraic multiplicity of 0 equal to 50. That is 0 will occur 50 times. Okay. So 0 will occur 50 times. Now if we see trace of the matrix J, it is sum of the diagonals, which is 1 plus 1 plus 1, 51 times, which is 51. Now we also know that trace is same as sum of eigenvalues. Okay. So in this case trace is 51. So sum of eigenvalues is also 51. So 0 occurring 50 times. So what is the other possibilities of eigenvalues? There are 51 eigenvalues. It is 51 by 51 matrix. So there are 51 eigenvalues. So 0 occur 50 times. It means the only non-zero eigenvalue this is same as 51, because we need to subtract all other eigenvalues from 51. So all our other eigenvalues are 0 actually, because multiplicity of 0 is 50. So we just need to subtract all other zeros 50 times, but it will not change, so we will get 51 again. So from here it is clear that we have finally obtained all the eigenvalues of J. So eigenvalues of J, it is either 0 or 51. So 0 occur 50 times. This is called algebraic multiplicity. Now, what is determinant of J minus R? Now observe that if, so I should state a fact, it is very useful. So if lambda is an eigenvalue of A, then it is clear that lambda square should be an eigenvalue of A square. Why this is true? Eigenvalues of A square. Why this is true? Because there exists some V non-zero such that AV equal to lambda V. And if you again apply A, then we have A square V on the left. And this is same as A times lambda V. That is lambda times AV, which is, but AV is same as lambda V, right? So this is lambda square V. So from here it is clear lambda square is an eigenvalue of A square. So similarly you can claim that lambda to the power n, this is an eigenvalue of A to the power n. Now if you add all this fact, then for any polynomial of A. So if you take this kind of polynomial, a to the power n plus some, maybe some a0 a to the power n, a1 a to the power n minus 1 plus n equal, if you take this polynomial Pa, then eigenvalue of this polynomial, it will take the form a0 lambda to the power n, a1 lambda to the power n minus 1 up to n. Okay, so if A satisfy any equation, then the eigenvalue lambda will also satisfy that equation. Okay, so from here it is clear that eigenvalue, back to this problem, eigenvalues of j minus I. So what are the eigenvalues? It will be simply subtract. So j minus I, you can see that this can be written as j, you can this can be written as, this is same as j minus I, j to the power 0. Okay, but what is the eigenvalues of identity? This is simply, eigenvalues of identities are all 1. Okay, j to the power 0, eigenvalue of j to the power 0 is same as eigenvalues of, what are the eigenvalues? Those are actually 51 and 0. So those to the power 0. Though 0 to the power 0 does not make any sense, but you can easily see that eigenvalues of identity matrix are the diagonal entries, so all are 1. Okay, so simply we subtract eigenvalues of j, eigenvalues of I from eigenvalues of j. So that is same as subtracting 1. This is minus 1, this is 50. This is 50 times and this is 1 times. So we have finally got the answer. Alright. So determinant of any matrix is same as product of eigenvalues of j minus I. But what are the eigenvalues? Minus 1 occurring 50 times. So minus 1 to the power 50 times another thing is 50. But minus 1 to the power 50 means it is plus 1 into 50, which is 50. So the answer will be 50. Okay. So the last question. This is the main thing you need to use for those kind of questions. It is very useful. That is for any polynomial Pa, for any polynomial Pa, matrix polynomial, this is an times I. Eigenvalues are P lambda, where lambdas are eigenvalues of. So let us solve the last question. So here T be the linear operator on R5. So you can see this is, and it is represented by this 5 by 5 matrix. Now the question is, which of the statement is correct? Where are the statements? So the statements are not given. Let me tell what are those statements. First option was option A equal to 0 and BCD non-zero. Option B, this is same as A, B, C are 0, D is non-zero. Option C, A, B, C, D, those are 0. All of those A, B, C, D are 0. And the last option was B, C, D are 0 and A is non-zero. So let us check what is the possibility. So it says that this question says T is an operator represented by the standard basis. Then A is diagonalizable if only if this. Which of the following are true? So we need to see which of the following are true. So we can easily see that it is an upper triangular matrix. Therefore, all eigenvalues are diagonal entries. So diagonal entries are 0, 0, 0, 0, 0. So those are eigenvalues. So 0 occurring 5 times. Algebraic multiplicity of 0 is 5. Now, so 0 is the only eigenvalue. So we must have 5 linearly independent eigenvector in order to A to be diagonalized. Right? So corresponding to 0, A is diagonalizable if and only if, what is the condition? That corresponding to 0, A must A has, here a value of n by n means 5, so it is A has 5 linearly independent eigenvector. That means if V be an eigenvector and eigenvector, then V equal to 0, right? A minus lambda I times V equal to 0, but here value of lambdas are 0, that is a minus 0 I times V equal to 0, that is A times V equal to 0. But A times V equal to 0 means, this means V is, So A times, so let, instead of writing this, let V equal to this vector B1, B2, B3, B4 up to B5. Then if we multiply with A, we can see A times V, this equal to same as A, means it takes the from all are 0, and above the diagonal there are non-zero, there are entries A, B, C, D, and all rest of the things are 0. Times, instead of B1 we should have written, okay, so B1, B2, so we are solving this AV times A times B equal to 0. So we have written A and we have B, but from the first row we are getting A times B2 equal to 0. From the second row we are getting B times B3 equal to 0. Similarly, C times B4 equal to 0 and D times B5 equal to 0. Okay. So if you assume at least, if you assume, actually we don't need those kind of steps. So instead of writing all of these, I should have said directly that from here, if you see the matrix A, instead of solving those kind of, it is nonsense, not making any sense. So if you just see the matrix A, you can see that rank of A, it depends the non-zero values of A, B, C, D, right? Those are pivot entries. This is already in a row reduced echelon form. This is row reduced echelon form. Therefore, rank of A, it depends if the number of non-zero entries from A, B, C, D. Okay. Rank of A is same as number of non-zero entries among those A, B, C, D. Right? So, if we see the therefore solution of this system, solution of this star, number of linearly independent solution, linearly independent solution of star, this is same as nullity of A. That is same as, it is 5 by 5, so it is 5 minus rank of A. But we must have 5 linearly independent solution. So this equation must have 5 linearly independent solution. That means this should be 5. By condition 5 minus rank A, this must be 5. Because we must have 5 linearly independent solution in order to have 5 linearly independent eigenvector, that is diagonalizability of A. So it is equivalent to saying rank of A equal to 0. So rank of A equal to 0, this means if any of this A, B, C, D is non-zero, then rank cannot be 0, because if suppose A is non-zero, then rank will be 1, only A. Suppose A, B, 2 are non-zero and C, D are 0, then rank will be 2. So it must ABCD must be all of those ABCD must be 0, right? So this is the correct solution. Diagonalizability means, so remember this mm, fact or this theorem. Diagonalizability means we must have n linearly independent eigenvectors. So corresponding to eigenvector corresponding to 0, it means it will satisfy this kind of system of equation. But this means this system of equation have 5 linearly independent solutions, because we must have 5 linearly independent eigenvector. But 5 linearly independent eigenvector is only possible when ABCD both all of those are 0. If one of this ABCD is non-zero, then we'll have an we'll have something in the solution space, right? That is, this A must be 0. This is the main thing. What happened? Okay, so the final thing is A must be 0. Otherwise, we will not have 5 linearly independent solutions. Okay, so this is the only answer. So okay, let me stop here.